So again, statistics again. So I just want to review the whole point. And this may seem like, well, what does this have to do with testing? Because all we're going to, really a lot of classical test theory is taking the ideas that we have behind stats like the mean or correlation or things like that, and just applying them to test items and then making decisions about the quality of those test items based on that information. So something like an item's difficulty really is just the item's average. If the average is high, the item is pretty easy. If the average is low, the item is pretty difficult, right? So it's just an idea of thinking about things like averages, standard deviations, correlation, regression, those types of things in a different way. Things like percentiles, right? Using percentiles to sort of to score people like they do on the things like GRE. It's just, but it's nothing new. It's just we're using it in a different way for a different purpose, but it's all the same kind of stuff. So what's the main, one of there's really, few uses of statistics if you bring it down to a higher level. We want to organize and we want to find patterns. That's a big thing, right? So we want to try to organize data, because when it comes down to your general public, they don't like numbers, right? Numbers freak people out. So we're always trying to figure out a way to reduce the amount of numbers, to replace numbers with pictures, like little colorful bars and things, or circles with pies in them or something, because they like that better than seeing just numbers. Because numbers somehow make people afraid or something. There's probably some kind of phobia. People, I don't know. There's something weird. People just, I don't know, numbers freak people out. So oftentimes I want to see the numbers. I don't care about the colorful graph. I want to see what the numbers are. But again, that's just me, I guess. So we want to take things that are sort of incomprehensible or oftentimes too large, to really try to understand it and convert it to something that either summarizes the data, graphs it, and tries to make some sense out of it. You've probably seen a ton of this with all the COVID-19 data. You go on to any social media, you're going to see just tons and tons and tons of graphs. Oh, this is the 7-day average graph. This is, they got the graphs of death versus the graphs of new cases. It's all kinds. People are just overlaying data in all kinds of ways to try and make different points. And the same people, or different people, are using the same information to try to convince you that things are getting better. Somebody else trying to use the same information, trying to convince you that things are getting worse. Look, here's a graph that shows why you shouldn't wear a mask. Here's that same graph, and this is why you should wear a mask. It's nuts, right? So everyone's trying to find their best way to figure out. There's actually someone interesting. There's somebody in our college, and here at CISA in geography, he put together. He was one of the first ones to put together like an interactive map showing where the outbreaks of COVID-19 were happening. I think around the country, but specifically around LA County. So a lot of those, if you've seen interactive maps that show like hotspots and things like that, it's like they have come out of a researcher here at CISA and actually put that together. He's a GIS, the Geographic Information Systems sort of scientist, and he sort of started putting that together right when it first started happening, and I think he's got it so it just automatically updates. So trying to make data more palatable, right? So that's what we're oftentimes trying to do. How do we take data, give it to people so that they're not freaked out by it, they're not overwhelmed by it? We also sometimes want to go beyond that. We want to actually extract information out, be able to make predictions, be able to do some kinds of hypothesis testing, right? Like even with the COVID-19 thing, you got, if you know at some point in a graph, for wherever you are, it doesn't make a difference, but some point where you start off wherever you're starting to measure, and you know that it's sort of doing this, right? You see the slow climb. You want to see things like there's these lagged sort of graphs where you want to be able to see like, all right, if here's where the sort of mandatory mask thing starts, right, for a county someplace, and that's happening here, it's going to continue to go up for likely 10 to 14 days afterwards, and then you should see then if this really works, then you should start to see a drop in the thing. So being able to use data to test hypotheses, like does mask wearing actually make a difference? Again, assuming that people actually follow the rules and actually do it. But so relationships prediction, being able to look at different groups of people. You can look at whether or not younger or older people, if the masks are working differently. You can start to take the collapsing and sort of summarizing of data and start to then use that to infer meaning from the data, which then can lead to prediction and hypothesis testing, that sort of thing. All right. So this is like a goofy example. So it's like you imagine I stood outside of a movie theater, right? Again, example is not super relevant, seeing as how movie theaters are mostly closed. But let's say I stood outside of a movie theater when they were open, and I just asked people what kind of movie they saw, and then to rate the kind of movie they saw, like from scale of 1 to 10 or something. So again, it's disorganized. The whole point here is it's hard to actually extract any meaning from this unless you sort of start to reorganize and start to summarize data some way. So you can start to see that whatever's going on, there must have been a decent like horror movie that was going on at that particular time, because everyone sort of rated that one much higher. That's hard to see, at least hard to confirm just looking at the data. Now this is not very many. Imagine this is hundreds of thousands. Imagine this is data from like Netflix, where it's in, it's like 11 billion, bits of information an hour or second or something. They have so much data, it's crazy. Or Amazon for that matter. There's no way really to sift through anything unless you have something that can go through and actually take something like an average or something to reduce the data down and start to find patterns and things. And then it's even better because see, these still include numbers, which people don't like for whatever reason. So let's turn those numbers into colorful bars. People like that a lot better. Look, this is the same information. It tells you the exact same thing that this does. This just has a pretty blue or purple or whatever color this is. It makes it so much snazzier for people. People like this a lot better. So many times I'll written reports, evaluation reports, it'll be a table of numbers and stuff, and the person will ask me, "Oh, could you turn it into a bar graph or pie chart or something?" And I'm just like, "Yeah, I guess I'll do that. It's the same information, but look, I can now see that this bar is higher than this bar." Whatever. I don't know. It never quite makes any sense to me. But again, people accuse me of being this math geek or whatever, which by the way I'm not. If you had told me in high school that I would be teaching stats, at the college level or graduate level, I would have laughed at you. But I sort of came at it in a very odd way. But this, for some reason, it tends to be more attention-getting, tends to get information across. And there are lots of times, and I'm sort of oversimplifying to be funny, but where graphics like this actually can tell you a lot more than this, because you can see trends and patterns that something like this is not going to tell you. But anyway. Inferential statistics takes it a step further. We actually want to make inference. The way we typically do that is to try to infer meaning from a sample to a population. So there's all this sort of population and sampling procedures that we go through, and that's all like the 100B or whatever the research methods course you took. It's oftentimes a lot about that. So samples are taken from populations, and the reason why it's called inferential statistics is because we're doing stuff to the people that we have, the sample that we have. We have those. Let's do something to them. Let's mess with them. Let's give them a treatment, placebo. Let's do whatever we're going to do to them. Let's electroshock therapy, whatever we're going to do to these people. And then we're going to then infer meaning back to the population they came from and say, look, we were able to randomly select these people. We were able to get a decent random sampling of folks from the population. So they should be a fairly decent representation of what's going on in the population. That's how we sort of make our inferences. Right, so I got this little goofy thing here where like population is the complete set of people, animals, events, or objects that share a common characteristic. So it's like everyone in the largest circle, right? And the sample is just some subset of those folks. And a lot of what goes on in 100B or your research methods course is really all about this group. It's all about how do we make sure that this group actually represents the larger group. So when you talk about things like stratified random sampling or cluster sampling or all these different methods, we're trying to make sure that these people in this smaller subset reflect everyone who's in the larger the larger data set. So there's a lot of work that goes into that. Things like simple random samples aren't always possible, so they get more and more complicated. But the idea here is that you have this large population that have all kinds of different people in there, whether it's genders, ethnicities, whatever, languages, educational background, whatever. They represent some spectrum of all kinds of people that exist in some certain proportion, and you want your sample to be representative. So representative means that your sample contains about the same proportions of people in the population, which make it sort of so that you can make the inferences a little easier, right? And when you can make remember, like, so if I do a good job of picking my sample and making it representative, that makes this sample what relative to the population? Do you remember? I'm just trying to get some responses from you all so that make sure you're awake and stuff. Make sure I'm awake. Yeah, so if I do something to this group, I give them a treatment or whatever I do to them, there's now a really cool term that I'm able to use when describing this group as it reflects back at the whole population. I'm being super vague. I'm just trying to get your brains to, like, dust off the brain cells. I always picture like a little squirrel cage in there, trying to get the squirrel going. We spend all kinds of time trying to make sure that we select a sample that is sort of valid and representative and all this stuff because we want it to be representative of the population, but we have a term. It's oftentimes the exact opposite of what the focus of most research methods courses. They usually are trying to focus on the validity. All right, you want a lot of internal validity in your study. I'm actually referring to the fact that this is very representative of the overall population. It makes it what? Relative to the population. Yes. Who said that? Nice. Like basically like a silhouette. You're like, hey, what's up? So yes, so generalizable. So the terms like externally valid or external validity and generalizability, those two things are more or less interchangeable. So the better job I do of making this sample representative, the easier it is to generalize to this bigger population or to other populations that may be similar. So generalizability or external validity. Or internal validity has to do with the way in which we define our samples, like break them up into treatment and control groups and those kinds of things, and to control for all the extraneous variables, those kinds of things all go into sort of internal validity, which makes our conclusions more or less causal, right? Trying to look at causal conclusions, where generalizability has more to do with how much does this sample really represent our overall population. And oftentimes those things are at odds. Right, the more we limit things down, trying to get more internal validity, the less our sample is like our population. So there oftentimes it's a give and take between those things. Okay. So again, tell me if I'm going too slow or whatever. Ask questions. Tell me to speed through things, whatever. Just because I'll just keep rambling on. I'm literally like in a tiny room talking to a window, so I'll just keep. Let's keep rambling on. Anyway, so this is all just sort of summaries of stuff. Population big, sample small. The idea is the sample is supposed to represent the population. This is some subset, right? When we talk about populations, we talk about parameters, population parameters. So the mean of a population is a parameter, where the mean of a sample is a statistic. So even the term statistics is referring to the fact that we're often, or almost always, working with a sample of people and calculating the statistics on those samples so that we can infer meaning back to the corresponding parameters. Parameters typically are written in Greek letters. This is mu and this is sigma, so lowercase sigma. And this is X bar, but sometimes it's not just X bar. Sometimes a lot of books have changed into using sort of M sub X as mean instead of X bar. Whatever. It's usually written out as some Latin letter as opposed to a Greek letter. So you may see it as S, or sometimes you'll see SD, depending on where you're looking. But these two things they correspond, where this is the population value. This is the sample value that we're trying to use to estimate this population value. So the inference is always going this way. We're always trying to go from the sample and try to infer meaning back to the population from our sample. So that's where the term sort of inferential statistics comes from. I should just say inference. Trying to make some kind of inference there. This all sound familiar? Ringing a bell? I hope. All right. I don't know why I'm looking at Yin in a video, and you're making me hot because you are like fanning yourself as if you're warm. And I didn't feel warm until I noticed you had the fan going, and I was like, now I feel warm. But maybe me, it's probably because of the lights and stuff. And I'm wearing a long sleeve shirt like an idiot. Anyway, but so by the way, you'll notice like you probably think I have a strange fashion sense or something. So you're gonna see me wearing the same shirts all the time, and it's on purpose because if this is a dark solid shirt, I can write basically in front of myself, and you can see when I'm writing. Or if I had a light shirt on, or if I had something that had writing on it or patterns, you wouldn't see it very well. So this is sort of like me trying to mask the fact that I'm here. All you see is really my head. But so it's funny, I'm wearing this long sleeve shirt to cover my arms and everything else. So I'm literally wearing a long sleeve shirt with a t-shirt underneath and shorts. So when I go to the restroom and I see colleagues, and they got a really odd dresser because I'm wearing a long sleeve shirt and shorts. I figured, hey, you can't see my legs anyway. Why wear pants? That's one of the beautiful things about the pandemic and lockdown, right? Is it freed us from all of our pants. We don't have to wear pants anymore. Like you just show up to meetings and stuff, just pajamas or whatever you want. Okay. Questions about this stuff? Population sample. Things are pretty straightforward. So the whole point, of inferential statistics is trying to take samples, do stuff to them. In this example, it's like, right, if we can manipulate somehow the amount of time studied for a course, like 100A or something like that, it doesn't make a difference, to the person's exam score or score in the class or something like that, their grade. So, we can actually, we can either just measure the amount of time that people do this, so we can manipulate it. The difference being there that if we just allow people to do it on their own, like decide how long they're going to study for, that's actually going to be more generalizable. It's more realistic. That's how people were doing it anyway. It's more like the sample, more like the population as it was. If we manipulate these things and tell people you can only study 1 hour a day, or you have to study 5 hours a day or something like that, it's a manipulation which becomes more internally valid, but then you lose some of the generalizability because these people wouldn't have done that on their own, necessarily. All right. Sometimes manipulation is not possible, so we still try to make inferences for things like prediction. So can we establish a relationship, like number of cigarettes smoked per number of cigarettes smoked per person, leading to coronary heart disease or lung cancer or something like that. The level of child abuse in the home and the severity of later psychiatric problems. This has been studied quite extensively. Early childhood trauma leading to later trauma or later disabilities and disorders. This is not something you can actually test experimentally. So no matter what they find or how they claim or what things they find connected, they actually can't ever get to the point where they can say cause, because you can't manipulate it. I mean, imagine that. All right, we got 50 kids. We're going to abuse 25 of them randomly, right? We'll make sure it's random. We're going to flip a coin. So it's, we're not like going to pick the kids that get abused. We're going to let the coin decide, abuse half of them. The other half, get treated nicely, and then 30 years later, we'll come back and see how they're doing. You can't. It's not really going to be possible, right? So there's a lot of focus, and I'm going to say this, as someone who's probably made the same claim before, but there's a lot of focus on experimental design, on doing the manipulation, on being able to get to some kind of causal conclusion, some kind of causal connection between a predictor, an IV, and a DV. But a lot of social sciences, I think it's sciences in general, have been moved forward faster and have made bigger leaps, not because of the experimental design stuff, but because simple predictions, simple regressions, right? Because if a kid has had a childhood trauma and that predicts they later have, psychological issues, I don't have to know if it's the trauma that's causing those issues. If I know that they're related, I can develop an intervention to sort of help. So I can identify those kids, intervene, and lower the chances of psychological trauma and stuff later on. So it doesn't matter that I can prove that they connect. As long as there's a strong enough connection there, I can actually then start to work towards intervention. Anyway, there's lots of weird things with the use of the death penalty and level of crime. Places where they implemented the death penalty actually had increases in the number of crimes punishable by death, which doesn't make any sense. Death penalty was supposed to scare people, right? It's supposed to be like a scared straight thing. If you know that you're going to be killed because of things you do, you're supposed to not do them. Except in those areas, oftentimes the number of crimes went up. So there's all kinds of weird predictive correlational kinds of things that actually make that move science forward without it being a sort of experimental design. So we use correlation quite often to make inferences about relationships. It's just you have to limit the kinds of inference you can make, right? If you learn nothing else from your 100A or intro, stats course or whatever, is that correlation does not equal causation, right? So that's like that's the one thing people take away from there. Same thing with regression, prediction, correlation, showing that things are related. You're not showing necessarily that one thing causes the other, but the fact that they are related means there are things you can do, interventions that can be taken. You can change the prediction and trajectory without having to prove that they are necessarily causal in relationship, right? And this is just talking about the correlations go from -1 to 1. So if you're ever reading something and they're like, oh, these two things are correlated at 2.53, that's not right. You can't have anything more than 1. The correlation, they usually meant that it was prediction, it was regression. So how we're able to do a lot of stuff, prediction, correlation, the kinds of analyses that we can use, whether we're using something like an ANOVA or a t-test, or did anybody ever learn of things like the Mann-Whitney U or the Wilcoxon-Rank sum test, or what's a bunch of other ones? There's a sign test, and there's some other ones I'm blanking out on. These are all sort of tests that correspond to the tests that we typically teach, like a t-test or a ANOVA, but they are non-parametric, meaning that the kind of data they use are sort of nominal or ordinal, where t-tests, ANOVAs, and that kind of stuff require interval ratio level data. So oftentimes you probably heard of like the chi-square goodness of fit test, or those kind of things may have been taught in your stats courses, and those get at the non-parametric stuff because they're oftentimes nominal ordinal data. But if you're trying to compare things that are interval ratio, usually you can use t-tests or ANOVAs or any number of parametric or tests that assume like normal distribution, those kinds of things. So you've probably been through this a bunch of times before, but the difference between nominal, ordinal, and interval ratio, I mean, you know what the differences are, how those work? All right, as you think about it, I'll drink something. So far, so good. So nominal really looks at like qualitative differences. So nominal, even though we say that, oh, these are different levels of measurement, nominal is not a measurement level, really. It's like the absence of measurement. It's just to say that like these things go together, right? We're going to call these people, males because they share DNA, or not DNA, but chromosomes or whatever. And these ones are females, right? These people have similar beliefs, so we're going to call them conservatives. These people have these are the liberals, right? So it's a qualitative difference only. The reason why it's called nominal is so we're just giving names to things that are similar, right? We're just naming stuff. That's it. The categorical differences only. So yes, ordinal. Then add some order. So there actually has to be something different. There has to be some more or lessness to things for ordinal to work. So you think this is like, again, categories. This is like runners in a race. First place, second place, third place, fourth place. So you know that one is more or less, than the other, but you don't really know by how much. You don't know how much faster the first place winner was to the second place winner or whatever it is. You just know that there's an order. With interval, you take the qualities of nominal ordinal and you add an additional quality, which is the differences between the orders, the numbers, are now actually fixed width. I mean, the distance between the first and second place runner would be the same amount of time as it is for the second and third place runner, to the third and fourth place runner. Like everything is now equally distant to one another. So there's a fixed amount of more or less you get between each of the values that you don't get in ordinal. So for something to be an interval level of measurement, all the numbers have to be equally distant apart, or the amounts of change have to be equally distant. And then the only thing you really get with a ratio that's different, because ratio contains all of those, nominal, ordinal, interval, all those qualities, plus, let me know what the difference is. What's the last thing you get with a ratio? They can, but there's a reason why. And it's going to sound, it may sound sort of odd, or surprising at first. So if I'm going to take, so we're used to numbers being numbers, right? So I can take a number 4 divided by the number 2, and it equals 2, right? But in order for that to make sense, think about this. You guys are seeing like Likert scales, right? So you got like disagree. Like, you're seeing these kind of scales to agree, right? So now think about those numbers in that context. If I answer 4, whatever this question is, 7 is totally agree, 1 is totally disagree, 4 is in the middle between disagree and agree. If I divide 4 by 2, I get 2, which tells me that if I answer 4, I'm twice as much in agreement as I am to number 2. Right? So to answer 4, I'm 2 times as in agreement as I am as someone who answers number 2. Same thing if I answer 6, I'm twice as someone who answered 3. I'm 3 times someone who answered 2. None of those make any sense. All I know is that someone here answered that they are more or less than somebody, but I don't know that by answering 6, I agree twice as much as someone who answered number 3. It doesn't really make any sense. It's not really a meaningful ratio. For ratios to make sense, there has to be a realistic anchored 0, which means there can't be anything below 0. So Likert scales don't count. Likert scales don't really work as ratio level data because I could change these numbers to being -3, -2, -1, 0, 1, 2, 3, and they mean the same thing. The numbers actually don't really matter. So to be ratio, you have to have a realistic 0, where 0 means that whatever you're measuring, whatever you're looking at, is absent, that there's none of it. Then, if you have a point where this point means you have 0 of it, then if I do respond to 2, someone who responds 4 is twice as much as I have, because there's a point where it's anchored. The point where it actually means something to have a 0 point on the scale. If I don't have that, then the best I'm going to get is interval. I can't have a fully ratio scale without it. All right, so you have to have a realistic anchored 0 at some point on the scale. Actually, not at some point, at the one side of the scale. So lots of things we think about that, our interval, but not ratio. I was thinking like temperature. Temperature is probably a really good example of that, because especially in Fahrenheit, 0 means friggin' nothing. Like, what does 0 mean? Right? 32 is freezing. So 0, I'm sure, means something. It did at some point. It was like the freezing point of something. But 32 degrees is the freezing point of water. In Celsius, 0 is now the freezing point of water, but you can still have below 0 temperatures. So 0 is not really meaningful in terms of being an absence of temperature. The closest you get is the sort of Kelvin scale, where you get down to 0 Kelvin, then particles stop moving. Right? So it's so cold that even particles can't move. Then maybe that's, you got sort of then you could say that some temperature is twice another temperature, or something like that, where, if something is, imagine saying, oh, it's 80 degrees, that's definitely twice 40 degrees. It doesn't even make any sense to think that way. We don't think about temperature as being double, the amount of another temperature, because it doesn't really work in that way. Questions about that stuff? This is where things get on. Oh, go ahead. Sorry. It's at best going to be interval. I would argue most of the time it's not even interval. That's a different story. Most of the time, these Likert scales are really just ordinal. But there was a bunch of studies done, like in the 60s, 70s, sometime like that, where they showed that as long as you had like 7 or more choices, that it could be treated more or less as interval. But it's a whole other issue, because it's not. I can actually show you what the issue is, because I think I have a slide about it. That we tend to just think of these scales like Likert scales and stuff like that. We use them a bunch. They become a sort of staple in psychological research. I think it's because we use them often enough. So anyway, I'll come right back to that. The issue with it, because I forgot I had these in here too. All right, so ordinal things just change in terms of size. I know C is bigger than B. I know D is bigger than C, but I don't know by how much. It's not consistent. When it comes to interval of a measurement, I can now subtract things like the difference from it. So this isn't visually true, okay? But the difference between C and B, right? So C is 1 unit larger than B. D is also 1 unit larger than C. So there's a consistent growth. These boxes do not represent that very well. But the idea is that the differences between here, it represents the same change from each unit to the next unit, which is different than ordinal, where that consistent change isn't there. Okay, back up. So this is what I was talking about a second ago with interval level measurement. It's not that the consistent change has to happen between the numbers. Right? Going from 1 to 2 is obviously a 1 unit change. Going from 2 to 3 is obviously a 1 unit change. That's not the problem with like Likert scales and things. It's actually that whatever we're hypothesizing that change represents. So imagine this is IQ and this is intelligence. That going from 101 to 102 in IQ represents a change in intelligence, an increase in intelligence. Well, that same increase in intelligence should be consistent going from 102 to 103, going from 103 to 104. It should be the same change in the abstract sort of concept we're trying to measure. That's what makes it an interval. Not that the numbers are equally distant apart, but it's the change in the concept that is actually consistent. It makes it interval. That's why I'm saying that oftentimes Likert scales are not very, very, very interval. So this is what starts to happen. This happens even with things like intelligence. at the right around the mean somewhere, this 100 point down here, let's say this is 100, 101, 102, right? The change may be actually pretty big. Going from 100 to 101, you may actually get big changes. But as you get up into higher levels, let's say this is like, 130, 132, 133, you start into the higher IQs, the change between them may not seem very big at all. The actual change in intelligence may be actually very minor. Another way to think of that is, think about someone on the low end of intelligence, again, towards where they used to sort of consider cutoffs for mental retardation. Differences in those numbers going from like 70 to 71, 70 to 72, you could probably notice the difference in intelligence in terms of who was a few points higher than the other, because it would mean probably quite a lot of gains in noticeable sort of intelligence. But if you got someone on the high end who's like super genius level, they're always going to seem like geniuses. You're not going to be able to tell them apart very much at all, because the change in intelligence becomes much more fine-grained. And then when that happens, where the scale changes, the scale stays consistent, but the amount of the abstract concept changing sort of starts to shift. It's not truly interval level measurement anymore either. Anyway, so a lot of stuff that we do is not really interval, but we treat it that way anyway. So anyway, ratios have meaningful 0 points. We said it already. It contains everything that nominal ordinal does, but it adds in the 0. All right. So it's the same exact thing. It's just that this 0 really means that there's nothing lower than that. Like that is the fixed point at the bottom of the scale that represents 0 of whatever it is you're measuring. That's the absence of that thing. So to have a true 0 point means you actually can take ratios like 4 divided by 2, and it actually does mean that this thing represents twice this thing, and that ratio actually then makes sense. Without that 0 there, numbers don't make any. The numbers really don't mean anything. They don't mean that same kind of growth, right? They don't really mean that. So you can't really assume that 4 is twice 2, even though numerically that's true. It doesn't represent twice the amount of the abstract change. Right? All right. Questions so far? No questions? That's fine. It's barely there. No, you can't see it. I just realized that this has a laser pointer on it. So I wasn't sure if it would show up, but you can sort of see it. Maybe? Can you see it? No, it doesn't work. Yeah, there it is a little bit. It's only like when it's directly at it, can you see it? Sorry, I'm like a cat, I guess, easily distracted by a little red light or whatever. So before we go on to the next part, I'm going to talk about this a little differently. So let's do this. So let's make this a little more interactive. So you have things like percentiles and percentile ranks. This hopefully rings a bell. What's the difference between them and how do we calculate the two of them? So in order to figure that out, let's actually generate some data. So tell me, so just throw out some numbers, doesn't matter what they are. Probably not too large, but some numbers between like 1 and 100 or something. 12. Okay. 34. Keep going. 6. Okay, go. 20. All right, keep going. 72. 32. Say again, 16. 16. You're like, sure. That wasn't what I said, but sure. 2, 4, 6, 8. It's 10. So 10 is good enough. So let's say this is our sort of data set that we want to use, right? And we'll just call this x. Okay, so x is equal to that. So there's two different things that we want to know. One, I have a specific number, like, what's your favorite number out of here? Let's say it's 72. I don't know why I went to that one, but let's say 72. Actually, 72 is not. That's fine. 70. I didn't want it to be the highest number, so 72. And I want to know what percentage of people or scores fall below this number. Right. So if I'm actually picking a particular number and I want to be able to look at the percentage of scores that fall below it, that's actually called percentile rank. We can find that with this this equation that I just forgot. I need to put this one, rank minus 5.5 over n times 100. Okay. So we can do, it's rank minus 0.5 over n, I think, times 100. Okay, so we can figure that out using that. Then the other way we often have to think of percentiles is I have a specific percentile in mind. Like if you're thinking about grades and things, like what score do I need to have to be better than 80% of the class, or 90% of the class, or whatever score you're looking into. That is looking at sort of figuring out the percentile, which is you have a specific percentile in mind, and now you want to know what number corresponds to that. So that is where x equals p times n, I guess n plus 1, will give us the sort of location of it. I'll talk about that in a second. All right, so it gives you sort of the location, like where to find that that percentile. Okay. Are you with me so far? So how do I find so let's go with the first one. So I want the percentile rank. How do I find, it says rank minus 0.5. How do I find a rank? What does rank mean? The reason I want to sort of make sure this is clear is because a lot of times when you got your SATs back, or if you're taking the GREs or MCATs or LSATs or whatever, you're going to get back and it's going to say your percentile rank is, and it's going to give you a number. And that tells you what percentage of scores were scored below you on that test. So it gives you an idea of how good you did. If that number is small, like 20 or something, that means that you did better than only 20% of the other people who took the test. The number is really large, like 90. That means you did pretty well. You did better than 90% of other test takers. So testing and psych testing and educational testing, aptitude testing, all those things are tied very, very closely to these ideas of percentages and percentile ranks and percentiles. So I just want to make sure we understand what those are. We're going to come back and talk about them later on. So what's a rank? So you're given a percentile rank on these tests, and they're based on the ranks of your scores. So you never ask, like, what does that even mean? That's exactly right. So if I take all these scores and I reorder them, so I'll just call this is X sort of ordered. What's the smallest one? 6. You help me out here. 12, 17, 16, 17, 20, 32, 57, 72, and then 82. So, by the way, you also accidentally showed another sort of funny quality about these things. Whenever I do this, if I ever ask students to generate numbers, there's like a weird unspoken thing that that people won't say the same number that's already up there. Like I almost never will get repeats in these things because people are like, oh, somebody already said 17, so I can't say 17. Even though you could have all said 17. There's no restrictions on it, but for whatever reason, people, there's a weird like unspoken rule that, oh, somebody else picked a number, I can't say that same number. So that's why there's no repeats. So we'll talk about that in a second too. So if I want to rank this, it's pretty easy to rank because with no repeats, it's actually fairly easy. They're literally the order numbers. By the way, aren't you guys amazed that I was able to learn how to write backwards? Anyway. It's pretty cool, huh? Yeah, you're like, wait a minute. I'm actually not, by the way. It's interesting. So, just like as an aside, the camera is over there facing me. So, if the way the camera would be looking at it, the way you would see it, everything would be flipped around because I'm looking at it. It's right for me. There's a little in line from the camera to the computer. There's a little device, a little capture device that actually flips it. So. You're seeing it the same way that I'm seeing it, even though it's being filmed from that side. So I'm not writing backwards. I just thought I'd mess with you for a second. So this is my right hand, right? And I'm sort of, able to write normally, and it looks pretty good on the other side. There's no way I'd be able to do that. So I think writing my left hand, it would be pretty awful. All right, ready? I have to go backwards. 6. It would not be good. It would not look right at all, I don't think. Okay, sorry. So once I have those ranks, I can pop this in here and figure out, all right, so 72 as a rank of 9 minus that 0.5. Divided by n. What's n? Yeah. So divide that by the number of scores. That's pretty consistent. And you'll notice that like at this point, like n and n are the same. Because, I may not be consistent in writing either lowercase or uppercase n. That's because with only one group, little n and big N are the same thing. Only when you have multiple groups, all the little n's add up to the big N, and they mean different things, but for now they mean sort of the same thing. So this is 10. So that's 8.5 divided by 10, right? All right. 8.5, so we're talking about 0.85 times 100 equals 85. So percentile rank of 85. So far so good? Good question. So let's decide, since we have let's do it twice just for fun. So it actually won't affect the 72 at all. I don't know why I just erased both of them. That was dumb. So let's say we have two 32s. I meant to erase one, I erased both. And let's say we end up having two 17s. Okay. So the way I would normally do it is to number them the same way, but then you have to decide what to do with the ties, with the repeats, so you can fix them. So both 17s can't have two different ranks. So use there's multiple ways of doing it, but the usual way is to assign the midpoint. So we go, this rank is 1, there's only one of them. This rank is 2. This is not going to get 3.5 and 3.5. That's still 5. This is not going to be 6.5 and 6.5. 6.5, that's 7. That's still 8, that's still 9, that's still 10. So what if there were 3 of them? Let's say it went 1, 2, 3, 4, 5, and this is 32, 32, 32, right? Well, 5, 6, and 7, 6 is the middle number, so it would go 1, 2, 3.5, 3.5, and then 6, 6, 6, 8, 9, 10. So you would assign the midpoint number to all the repeat scores, and then apply these numbers to the equation. And then I'll give you the actual percentile rank that you're looking for. Okay. So let's go back for a second to original. So this was 16. And this was 34. I think. Yeah, I believe. So let's go back to original ranks. It's sort of easier. And then how do I figure out the percentile? So let's think about a number, I don't know, 75%. So I want to know what the x value that corresponds to 75%. So the way that works is the p value here corresponds to the probability. So if I want 75%, that just ends up being the proportion, 0.75. So I want 0.75. I have 10 values, so 10 plus 1. So what's 0.75 times 10 plus 1? 0.75 times 11. 8.25. Okay. If the number we had come back was a whole number, like an integer, like 8 or something, then we'd be done, right? Because if it was just 8, it would tell me that the value is in here, right? If it was just 8, it was 8 is the location, the position in our data where we find the 75th percentile, so that would be 57. The fact that we have leftovers, this 8.25, means I actually have to interpolate. This is another fun word, interpolate. So to interpolate, we're going to start here. So the number 8 there tells me where to begin. This is sort of the location. This is like my start here. I'm going to start there. So I'm going to start with this number. And then I'm going to look at whatever number is in the next highest position, which is this one. So now my whole thing, trying to figure out the percentile for this, all the other numbers don't matter anymore. It's just these two numbers that matter. Because what this is telling me is the number I'm looking for is 25% or 0.25, the distance between the number that's in the 8th and 9th positions, right? So I'm trying to, look for 8.25 is somewhere here, right? Man, it's getting messy. 8.25 falls, 25% of the distance between the 8th and 9th numbers. Okay, so far so good. So how do I find that? How do I find a number that's 25% of the way between the numbers in 8th and 9th positions? Well, I take those two numbers. So the number that's in the next highest position, we'll call that like position 2. Right? Equals 72. The number in position 1 is 57. And I want to find their distance. How far apart are they? I just wrote 57 backwards. 72 minus 57, which is, I don't know off the top of my head because I think my brain fell asleep about an hour ago. 57 is 15. So that tells me the whole span, the 100% of the distance between these two numbers is 15 units, right? So there's 15 units in between those two. Okay? But I only want 0.25 of that. I don't want the whole thing. So I got to take that distance, and let's, I don't call this the proportional distance or something. 0.25 times 15. What's 0.25 times 15? No, it's not. Times 15. 3.75. Now what do I do with that? Exactly right. So I take 57 plus 3.75. It's ends up being, what, 60.75? And that's the number that is at the 75th percentile. So to recap that, right? You figure out whatever percentile you're looking for, like if it's 75, you multiply that into n plus 1, and you're going to get a number. The number in front of the decimal tells you your starting position. So you go to that number, and you look at the number, that number, and the next position. The two numbers that are in those two positions are now the only thing you really care about. You figure out how far apart are those numbers by finding the distance here, and then you use that proportion that's on the sort of to the right of the decimal, or actually I guess it includes the decimal. You use that to find the proportional distance, 0.25 times 15. This is how far away the number you're looking for is from the number in the first position. You add those two together, and you get the number. It's there. And that's because the number in the 75th percentile doesn't actually exist in the data. Is a number that's in between data points that you actually have, so you actually have to interpolate it. You got to find what it would look like or what it would be if you happen to have it. Okay. Now, there's a couple assumptions made by both of these. You may have been wondering, like, why? So, why do I subtract 0.5 here? Why does it rank minus 0.5 and not just rank over n or rank plus 0.5, or why the 0.5 there? Let me know. When you look at programs like Excel or other things where they actually calculate percentile ranks, this is the most common way they do it, subtract 0.5. But you can add 0.5, and you can actually just leave it and not subtract 0.5 out at all. It has to do a lot with, well, a couple things. What you're assuming. So with percentile ranks, the normal interpretation of a percentile rank is I want to know what percentage of scores fall below that score. So with our 72, right, we found out what proportion or what percentage of scores fall below 72. I don't want to include 72 in that percentage. I want to know what scores fall below that number. If I wanted to include 72, I would be asking something like, what is the percentage of scores that are at or below 72? And that's not usually what we want. Usually we want just below. So the reason why we subtract 0.5 is to actually take the rank, move it away from the number that we're talking about here, to capture just the numbers that are below that value and not capture that. Because if I don't subtract 0.5 out, a weird thing can happen. So go back to when we had ties. All right, so when we had like 32 and 32 here before, and these are both 6.5 and 6.5. If I leave it at the rank, what happens is the percentile includes one of them, but not the other. Right? Because it's saying 6.5 below, I'm actually capturing one number, but not the other number, which is sort of a weird thing to do. So if I subtract 0.5, it moves it outside of this, and I capture only things that are below 32. Right, so the 0.5 helps to move it away. It also comes back to those things like, if you remember real, I don't know if you remember talking about this stuff, but real limits. You know, it actually, the real limit between, say, 16 and 17, right, is 16.5. So a number that sort of divides if you're 16 or 17, right? You're either above that number or below it. So real limits, oftentimes half the unit. So you're moving it below that. If I were to add it, same thing here. If I was to add it, it actually would move it to right above the number. So I'd be capturing these values and below, right? By moving the rank just 0.5 up, I would now capture both 32s, and it would tell me what's the percentile rank of being 32 and below. So if I add 0.5, it includes the number. If I subtract 0.5, it leaves the number out of the percentage. Anyway, questions about that? I think we're quickly running out of time here. It's 3 o'clock. All right. There's, in the slides that you have, there's some more examples of this. Like if you want to, if you're still having a little bit of trouble grasping the percentile rank thing, there's some more info there, but probably should move on. Or if you have questions, you can always sort of email me. I'm happy to explain it some more. But I realize that percentiles, especially this idea of interpolation stuff, can be kind of challenging when you're first trying to wrap your head around it. All right. So again, like I said, there's more here about that if you want to. There's some interesting things, like if you heard of like percentiles and quartiles. Well, there are 99 percentiles that cut data up into like 100 chunks, right? So quartiles, which sometimes is surprising, I think, to people, there are 3 quartiles, which makes no sense just in a naming sense that if we want to cut things up into quarters, I want to have 3 of them. It's because up to Q1 is 1 quarter. Between Q1 and Q2 is another quarter. Q2 to Q3 is another quarter, and then above Q3 is a 4th quarter. So you have 3 cuts to make 4 quarters. It's sort of like if you had a loaf of bread and you wanted like 5 slices of bread, you wouldn't make 5 cuts, then you'd have 6 slices. You would make 4 cuts in the bread to have 5 slices. That makes any sense. There's also this thing called deciles. Deciles are just every 10th percentile is a decile. So D1 is the same thing as P10, and D2 is P20, and so forth. So deciles is another. You don't hear about deciles so much. People don't run around using deciles as a term. You hear quartiles more, but percentiles for sure the most. We just talked about that, and here again there's just explanation about midpoint ties and that kind of stuff. So instead of doing this way, I decided that we would just do it together. It's a little more interactively, but this is the same information. It's just just built into the slide. Some more examples. So for quartiles, you calculate quartiles the same way that you would calculate a percentile. You're just doing it for P25 specifically. P50 is the same thing as the median, right? So median is the number of the 50th percentile. So the median, Q2, P50, those are all the same thing, right? So a median is the number, it's another average value that we use, that it just is the center of the distribution as opposed to being the arithmetic average like the mean. So regardless of the number of scores you have, remember again, people are afraid of numbers. They don't like to see a lot of numbers, especially when numbers get like together in large groups. People really don't like that, right? They want to see small little groups of numbers. People find large groups of numbers, like if you throw like a matrix of numbers of people, man, people will freak out. So you got to keep the numbers in small groups. You got to keep them, in a sort of tame amount for people to sort of be okay with it. So if you start to get larger amounts of data together, people want you to reduce it down. Just tell me what the average is. Just tell me what the variability is. Tell me, what the shape is. I don't need to see all the numbers. I just want to know what's the central tendency like. What's the mean, the median, mode? What's the variability? What's the shape? Those three pieces of information. Now I have two numbers and potentially just a description, right? Normal, skewed, but two numbers. Instead of having hundreds of thousands of numbers, I can break it down to a whole distribution with just two. What's the mean? What's standard deviation? What's the mode? What's the variance? Those kind of numbers can describe an entire distribution fairly well, as long as they sort of meet certain criteria. Like if it's a normally distributed data set, the mean and variability are going to be pretty. Mean and standard deviation can pretty much give you an idea of what the data set looks like. If it's skewed, then you probably don't want to use the mean. It'd likely be the median, and some other version of the standard deviation that uses the median. But the idea is that these two pieces of information, along with the knowledge of the shape, can be enough to tell you all you need to know about a distribution. We talk about this all the time. People talk about the housing market, right? Oh, the median housing price in LA is whatever it is. It's ridiculous. And the reason why they talk about median is because if they talked about the mean, it'd be even more ridiculous, because all the really super high numbers would pull the mean even higher. So median housing price is usually what they talk about because of all the skewness. People are usually happy with just the central tendency and will ignore the variability, which is oftentimes a problem too. But